Okay, so in the first part of the course, we did a lot about basics of algorithms with a particular emphasis on how complexity changes with different types of algorithms. The second part of the course, we focused on matrices and linear algebra. Third part, which we just finished, was numerical integration as well as optimization. So for the next couple of weeks, we're going to focus on more or less machine learning, but we're really going to focus more on what I'd call very fundamental ideas of machine learning, why it's something that you might want to do, some of the basics of how these algorithms operate. So I'm not going to focus so much on necessarily the latest bells and whistles. I'm going to try to focus on simple things that maybe give some intuition behind how these super fancy big models work. Having said that, we will do neural networks probably the last week, but we're going to start by trying to make sure we understand how simpler things work. That way we can maybe view those as a generalization of more simple learning ideas. Okay, so we're going to start by doing supervised learning, which I think is probably the type of learning that's most familiar to many of us. This is the classic example of models that you give it a picture of a cat and it tells you it's a cat, et cetera, et cetera. So this is, I think when people think of machine learning, this is maybe their first thought. Although there are certainly exceptions that we'll see in a couple of course lectures. Okay, so supervised learning, the basic idea here, right, is that I have data, and each data point, so let's say I have n data points, each one is associated with some label that describes it. So I have a set of pairs describing my data. By convention, we're going to refer to data points with a big X, and we're going to refer to the labels, or the targets, or the outputs, whatever you want to call it. That's going to be our Y variable. And I'll use that notation somewhat consistently throughout these notebooks. And I'll just mention that this notebook, as well as some of the other notebooks that we'll see, are adapted from Pankaj Mehta's ML course, which is what we're using as our textbook. So the book has a bunch of notebooks that go through some of this. I made a couple of changes to match them up with the rest of the course and the notation, but the core content here was originally developed by Professor Mehta. Okay, so the kinds of methods that fall under the umbrella of supervised learning include things like linear regression, which many of us have probably had to do before, things like forecasting, so predicting the next point in a time series given previous points, as well as the more sort of classical examples of classification, like this image is a cat or a dog. And the idea that all of us have in common is that while the cat dog classifier is sort of an intuitive picture of what supervised learning is, on some level, you can think of forecasting as your X, your input being a set of points, and your Y, your output or target being the next point. Likewise, linear regression, you're trying to find a relationship between two variables where your model spits out a prediction given the inputs. So I'll mention that you've probably used supervised learning before in the context maybe of regression problems. So the way that I normally think about regression problems and supervised learning problems is that on some level, there's a generator or there's a process that maps X to Y, and our job is to try to learn to approximate that process. So if you're doing forecasting, an accurate supervised learning model effectively picks up whatever that underlying dynamical system is and can generate the next time point. So there's this idea of sort of generation baked into supervised learning. So to get started, we're going to start with the most simple supervised learning method that I can think of. This is something that it might seem very basic, but a lot of other methods are more or less generalizations of this, which is why it's good to start with this. So this is linear regression. So before we get into the algorithm, we're going to choose a problem that's particularly well suited to this algorithm. And this is going to be classifying different microstates of the Ising model based off of their energy. So the idea is that I have a bunch of spins. So that's going to be denoted by this element S. Those spins are arranged on a lattice. So J indexes each spin. Each spin can either point up or down. If the two spins point the same direction, they contribute a negative term to the Hamiltonian. If the spins point in opposite directions, then they contribute a positive term to this Hamiltonian. So in other words, this Hamiltonian, we want to minimize the energy. The lowest energy state of the system is going to be a ferromagnetic state where all of the spins are aligned. So in this problem, your data is going to be pictures of microstates which describe every spin on this lattice, which is either up +1 or down -1. So my input data, my x vector is binary. It's either plus or -1 for L distinct sites. And the question is, without access to this Hamiltonian function, can I effectively rederive this relationship just given a bunch of pictures of the spins and labels of this Hamiltonian? And the reason that we're going to use this particular problem is because you can just tell from looking at it that it looks like a linear problem. There's a linear relationship here. But having said that, that doesn't necessarily mean that it's going to be trivial to find a model that just given a bunch of pictures of the lattice will predict the correct energy. So there is going to be some subtlety despite the apparent simplicity of the Ising model as a system. Okay, so then the learning problem we're trying to solve is that I've been given some material that's a bunch of spins. I can measure every single spin state, so I can get microstates. My x vector is this big binary vector. And then at the same time, I can also do something like measure the energy of each state. So my data points are this S vector, which is going to be this binary vector, and my labels, our targets, are just the energies. And I want to find some general purpose function that if I then was given some new data point I hadn't seen before, some new microstate, I could then learn that energy just from my model that I've learned on all these snapshots I've been given. So can we learn effectively this functional relationship just given snapshots of the spins and the energies? Okay, so our first step is we want to generate a bunch of data to train on. So in the real world, you'd be using learning when you have some black box experiment where you're trying to relate microstates to energies. We need to simulate that experiment to generate data to work with today. So if you were actually using supervised learning in the real world, you probably wouldn't need to do this. This is just so that we can create a toy data set. So you can imagine this as I'm doing my experiment and collecting my data. So for this, I'm going to implement the Ising model. I'm going to have nearest neighbor interactions, which is actually the same as what this specifies here. So basically, I want to align with my nearest neighbor, but I don't care what my next k neighbors do, right? You still might see a tendency to align because this neighbor aligns with its neighbor down the line, but the actual interactions here are just nearest neighbors. Okay, so this is my implementation of it. The important thing here is that this J matrix has this nearest neighbor structure. If you actually go and you look at the matrix, that basically corresponds to having diagonal structure where the diagonal is off of the main diagonal of the matrix. And then all the other elements of the J matrix are 0 for nearest neighbor coupling. Okay, so that defines my model. And then if I want to just sample a bunch of states of this model, I'm just going to pick random binary vectors of up and down spins. That's all I need to do to sample microstates. And then because I'm trying to simulate an experiment, I'm going to compute the energy of each of those microstates using this J matrix and by explicitly performing this sum here to get my actual output labels, my regression targets, which are the energies. So again, in the real world, if I was using supervised learning, I wouldn't be able to do this calculation. I just would have a bunch of values of energy and a bunch of microstates. I'm just trying to simulate what doing an experiment might produce. Okay, so that's how I've set this up. Ising model, I sample random microstates and I compute their energies. Okay, so that's going to give me a data set where the input data has, in this case, 10,000 points. So these are 10,000 samples of different microstates. Each of those points is a separate x vector. That x vector defines the microstate, which here corresponds to 40 different lattice sites corresponding to up or down spins. And then every single one of those microstates has an energy associated with it. So my labels or target values are going to be just a single vector of 10,000 values. So the first index by convention is the data point. The second index for the input data is the dimensionality or the feature space. You can think of it as the number of features, where here the features are just up or down at different lattice sites. Okay. So we want to pick the right model that, given just the observation of energies and given observations of the microstates, it can learn to approximate this functional relationship. So then if I give it a new microstate, it'll give me the correct energy. Okay, so there's a reason that we might choose to use linear regression for this problem, and even for a problem where we didn't have access to the Hamiltonian. So the idea here is that I have nearest neighbor interactions, and so on some level you can write the energy as a double sum over the matrix elements of J. So J is a big matrix. It just so happens that for nearest neighbor it has a single dominant term on the diagonal and a bunch of zeros. If I just say that J was some generic matrix where I might have all sorts of interactions across the lattice, then I might want to write the Hamiltonian in terms of a sum over every pair of neighbors. So this is slightly more elaborate notation that this will reduce back to our original Hamiltonian for the case where big J of JK is a matrix with just that nearest neighbor diagonal. So this is a more general version of that. So the idea here is that let's say I have no idea what J is, right? So I happen to know from my simulation that it's nearest neighbors, but if I'm given a bunch of microstatic energies, I have no idea what the coupling matrix is. I have no idea that J has that nice sparse structure. So in that case, I would say that this calculation, right, where I took every pair, calculated its J interaction, and used that compute the energy, where J basically determines the favorability of the ferromagnetic or antiferromagnetic interaction between sites J and K. I could take this equation, it's a double sum, so I can always convert it to a matrix equation. So this is equivalent to writing my Hamiltonian as the dot product between my data matrix, which has the microstates, and the J matrix. So here I'm by convention, because I'm counting my microstates or input data in this vector X, my regression target is Y. Each of X is going to be this vector of microstates. So I've sort of switched notation there. So in order to do that, I need to correctly dimensionalize this matrix. And so this X is going to capture this idea that these matrices have sort of an outer product structure associated with them, where if I want to turn this equation into this equation, rather than just having X be a vector, I really need to have it be an outer product of the spin vectors. And the idea there is that this version of Hamiltonian is capturing interactions between all Sj and all Sk, where J and K are both indices that run over the lattice. So I could just isolate this outer product and write that as its own matrix. Then that matrix dotted with J gives me my Hamiltonian. So in other words, we can basically use some of what we know about the structure of this problem to basically take our microstate and write it in a form that makes this a nice matrix equation. The reason that you might want to do this setup is because this kind of immediately, without knowing J, it jumps off the page that I might want to use a linear regression-like approach. Because in principle, my linear regression, if I perform it on this, it's really the question of given a bunch of observations of this matrix, which is all pairwise interactions between spins, and given this J matrix, which is like the equivalent of the slope or this interaction matrix that we're solving for, given those two things, can I get the correct set of targets where that's the energies associated with it? So if I take my problem, I say it has nearest neighbor structure. I don't know the interaction matrix, however, I can write this linear regression problem as the problem of finding this J matrix, given this sort of extruded matrix representation of the microstates that X encodes. Okay, so X is just a tricky way of rewriting our data set here in a way that really highlights the pairwise interactions are really what are going to matter for this problem. Okay, so I might just mention that I've done a couple of weird things here, right? One of them, and this is probably the most important one, is that I've applied a little bit of domain knowledge to this in order to know that I could do this reduction here. And that I've assumed that I don't necessarily know what the coupling among two spins are. I just know that they happen to interact in pairs, right? So if I had something like a higher order Ising model where you had intrinsic 3-body or 4-body interactions, this approach wouldn't work. So here I've just sort of used the fact that I know that spin systems tend to interact pairwise to apply sort of a prior to this. That's usually a good idea, is that if you know something about the structure of your input-output relationship, you should try to encode that into what your model sees rather than hope that your model learns it. It's good to constrain your model class around things that you know to be true. Okay, so that's a lot, but the takeaway is that I want to find this matrix J given a bunch of snapshots of microstates arranged in the way to form this outer product matrix X. That's the basic problem. And the hint is that we know from above that when we generate a bunch of data, that J, the correct answer is going to be J that imposes this nearest neighbor ferromagnetic coupling. But here we don't have J. J is the matrix of parameters that we're trying to solve for using linear regression. So this is a very direct way to see why linear regression would give you an actual physical parameter for a data set. Okay, so that's a lot. So let's take what we just generated out here. So this is us running our experiment. I wrote this down, but again, let's pretend that we don't have access to this class here. We just are given the output here. So the first thing that I want to do is I want to take my data and I want to convert it into a form that's a little bit more amenable for this machine learning analysis. So I'm going to use the fact that I have this sort of prior on the pairwise interactions, take all these microstates, find the outer products, and make that my data matrix. And I'm going to use the same trick we've used when we've had images or two-dimensional lattices in other contexts, which is that every single state, when I take the outer product, instead of being L equals 40 length vector, I take the outer product, it's now a 40 by 40 matrix. In order to make this just a little bit better behaved or a more consistent problem, I'm then going to flatten that matrix down so that I now have 40 squared elements in a vector. So I've kept all the information on my microstates extruded to the outer product. I've just flattened it because it makes more sense usually to have all of your features along one axis, and then your other axis is going to be the different samples that you have. So I take my outer products, then I flatten back down here. And so then I have X all, which is going to have a dimensionality equal to the number of samples. So here that was 10,000. And then the second is going to be the number of features, which here is 40 squared because I have 40 lattice sites. And then our targets, our regression targets, are just a single scalar per sample. And that's going to be the different energies computed under the Hamiltonian. So I'm going to go ahead and run those cells. And just to double check our sanity, we're going to check that xall.shape equals 10,000 by 40 lattice sites squared, the outer products. And then yall is that. Okay, so we've used an inductive bias to shape our data from our experiment in a way that's going to be amenable to the application of our model. Okay. So before we actually try to fit a J matrix to these snapshots of microstates and energies, we need to go through a few preliminaries. The first one, and we're going to spend a lot of time talking about this downstream, but the first thing that we're going to do is we're going to need to split all of our data into training and testing partitions. So the idea here is that I have a bunch of microstates. I have 10,000, it turns out, and I have 10,000 measurements of the energy associated with those microstates. Rather than using them all to fit J, we're going to hold a couple of them out, and we're going to basically use a subset of those 10,000. In this case, I use 400. I'm going to use 400 of those snapshots as my training data, and then I'm going to use another subset as my testing data. So I use only a part of my data to fit my model, and that's going to allow me to give a more fair evaluation of how well my model performs by running it on data that it's never seen before. Okay, so I split my data into train and test partitions. So X train, it now has length 400 by 1600, right? Because I still have the full number of features, I just have fewer samples. And then Y train will have it will be a vector of length 400, which is the energy of these 4 samples. And then these will have the same number of features as well, the testing partition. Okay. So I want to fit to solve this matrix equation, which is that I'm given a bunch of the values of this side, given a bunch of xi. I want to solve for j. So what I'm going to do is I'm going to basically give my model all the training data. We know how to do this analytically. It's going to perform this big matrix inversion to move x over here to give me an estimate of j. So this model, I'm using scikit-learn, which is the big machine learning model that we're going to use a lot. This implicitly just needs to do basically some matrix tricks to invert x-train to give me x-train, apply it to the output y, and give me the J matrix. Um, I'll mention that in the homework, we're going to actually try to implement linear regression. You can think about there's a little bit of fussiness here with this problem because X is not a square matrix, and so the inversion isn't uh, it doesn't have a unique solution, or it might be over or underdetermined depending on the number of features relative to the number of samples. You'll see that in the homework as to how you deal with those different cases. But for now, let's just assume that there's heuristics for dealing with a case where maybe you have might be more samples than features. So instead of computing an inverse, you have to compute a pseudo inverse where you might not exactly solve, you'll get an approximate solution. But importantly, all I want to do is just given a bunch of energies and given a bunch of microstates, I just want to find as best an approximation of J that gets me predictions of the energies that are close to what I saw. So I'm trying to minimize the difference between the right-hand side and the left-hand side. Okay. So I run that model. So this is standard syntax for scikit-learn, which is I construct my model, I fit the model. That's where it actually learns the parameters of the underlying model. And then I predict the values of the energies for the states that were in the training partition. So that's all that this loop does. So we'll give it a little bit of time to go through all that relatively fast. So for this problem, I know what the correct values of the training energies should be. And then I also have the predictions that come from this approximate J matrix I constructed. So here I'm just plotting the predictions versus the actual, and you can see it's a one-to-one match. So it turns out that for this subset of the training data, I had enough data that I was able to perfectly solve this problem in that I was able to perfectly recapitulate what was in the training data. So that could be good. That could mean that I'm done and that I've done everything. But you'll recall, as we've seen before in the linear algebra section, that one reason that I might see this is I could just be overfitting, right? Meaning that rather than learning the best possible representation of J that will always give me the right answer, I could just learn one. There could be multiple valid solutions for J, and I just happen to sample the one that works exactly well on the training data. So if the problem isn't so if my ratio of training data uh, to the number of parameters in my model is favored in terms of having too many parameters in my model, I could overfit and get a perfect result on this without actually correctly recovering my nearest neighbors coupling. Okay, so it looks good right now because my predictions are consistent with what I know is true for the training data. But again, this model saw the training outputs, so maybe it's overfitting. So here what I'm going to do is I'm going to use my testing data. This is that data that I split out before. The model, when I fit it, has never seen this data before. And importantly, in scikit-learn, as well as just generally when you build models, the only time the model updates parameters is when you call fit. No further changes to the estimate of J occur after this point. And so when I run that on the test data, which has never been seen before, then I get predictions that turn out to be not quite the same as the correct energies. So now it's clear that my model is overfitting a little bit because when I give it microstates it's seen before, it guesses the correct energy. When I give it microstates that it hasn't seen before, it maybe gets close to the right energy, right? There's clearly a monotonic relationship here, but it certainly isn't perfectly accurate. So in other words, I kind of solved this problem, but not perfectly accurate. So I probably don't have the best possible estimate of J. And this is why it's important to hold out data for supervised learning, because that's what's going to help me avoid spuriously thinking I've solved my problem when really I've just overfit. Okay, so it turns out to basically always be the case that for supervised learning, you can probably define a model that will give you 100% accuracy on your training data. It depends on how you've constrained your model, but for things like classification, you could always, for example, come up with a model that looks up the nearest training data instance and gives you whatever its label was. And so it turns out that if I've under-constrained my problem, like I have here, one possibility is that this J matrix just effectively stores everything it's ever seen. I give it a training data point and it just looks that one up and gives me the energy. And that's not great because then it hasn't actually learned anything about the input-output relationship. It's just sort of spitting back out what it's seen before. And in classification, there's a similar idea, which is that you can have something like a nearest neighbor classifier that just finds the nearest training example and gives you the output associated with it. So it always gives you 100% accuracy on train, but that doesn't necessarily work on test. So I'll mention that you really shouldn't read too much into training performance, other than it maybe tells you whether your model has sufficient capacity to capture all the variance in your training data. So one heuristic that people sometimes use is they'll deliberately try to increase their model size or complexity just enough that you're able to get 100% accuracy on train, so you hit that overfitting regime on train, but then you try not to increase model complexity much further than that. That's a way to sort of heuristically figure out if your model has enough parameters to capture what you're trying to do. Okay, so that's linear regression, trying to predict the energies of the Ising model given observations of microstates. Linear regression seems to have done pretty well, but there certainly appears to be room for improvement. Okay, so before I get into ways you might be able to do this better, I'll just mention that you can imagine I might just want to try to quantify, right? Because I sort of pointed at this picture and said, oh, that doesn't look very good. There's a lot of different ways you could actually try to score how well your prediction is doing. You could imagine, for example, finding the mean squared error between the true and the predicted. That's something that we've done before. For this particular version, because I'm just doing linear regression, I'm just going to use the coefficient of determination, so the R squared value. So that effectively is like a scaled version of the mean squared error between the prediction and the actual value, but it's going to be constrained to fall between 0 and 1. And I mention this because I think most of us who have done linear regression before have heard the R squared value being high is good or whatever. But basically, that's just making a statement about how close this plot is to just representing a line. Okay, so I have these plots here, so let's just boil them down to a single number. So as expected, our training R squared was 1, right? Because it looked like a line, so that makes sense. And it turned out that our test R squared was 0.5, which isn't terrible. It certainly is just a positive association, but there's clearly room for improvement. Okay, so I mentioned that I don't think we're really capturing the full structure of this problem. And the reason I don't think that we're capturing the full structure of the problem is not just because we had residual error on test, but also because I'm suspicious that our model isn't effectively constrained enough. And that's because if you think about it, this J matrix, that's a lot of different elements, right? Here my lattice site is 40, so I have a 40 by 40 matrix of free parameters. So it's 1,600 free parameters that I'm trying to pin down. I only used 400 data points to fit this. So you might suggest that what's happening here is that there's a lot of possible J matrices I could be using, and I'm finding one that works perfectly well in the training data, but that's not actually the best solution or the one that most captures reality. Really, I just happened to pick one of the most appropriate ones. So in other words, my J matrix is underdetermined here because I don't have enough training data. And so my J matrix, while it worked on train, the reason it doesn't work on test is because maybe I didn't provide enough information to constrain it down further. Okay, so for my Ising model example, I happen to have access to what the ground truth should be, right? Because my experiment here was a computer experiment, so I actually had the J matrix. So I know that my actual J matrix should look like this. So I mentioned that nearest neighbor coupling has this like off diagonal term. So these are all zeros and these are all ones. So that's captured in this matrix. So I know that this is what I want my parameters to look like. And so I can compare that to what my linear regression gave me, and I can start to see what's going on here, which is that my J matrix that spit out with vanilla linear regression is dense. It has values that are just a bunch of random numbers between plus and minus 1. It maybe picks up a little bit of what's going on here, but clearly this just found one of many possible solutions that perfectly fits train, but not necessarily the one that correctly matches reality. So using this idea of supervised learning as the process of finding the generator that maps inputs to outputs, here this is this idea that by finding J, I'm finding the parameters necessary to keep sampling my physical system to produce more microstate energy pairs. Okay, so what can I do to save my model and get a better estimate of J that is more like reality? So one thing you might think to do is just use a bunch more data, right? So I have 10,000 snapshots. I only use 400 to fit this. So you can imagine I could just crank up the amount of data to some comical amount, and that might help me slowly constrain this down until I get the correct answer. That would probably work for this problem, but it's not always feasible to just go and get an order of magnitude more data. So sometimes instead of having this issue or dealing with this issue in its native form, I'm better off saying I'm stuck with my given amount of data, but instead of just allowing my model to sort of wander freely through this parameter space, where the parameter space is the J matrix, instead I might further constrain my model so that the number of free parameters is effectively less than this L squared entries of this matrix. So this is going to be called regularization. And the idea is you basically just add a constraint to the problem that this model is trying to solve, such that it can't just pick any given J matrix consistent with the input-output relationships. The J matrix itself has to satisfy certain desirable features that I might want my model to exhibit. Okay, so regularization basically consists of finding the right penalty on the parameters of my model that cause the model to avoid overfitting or perhaps to match certain expectations I have about the elements of the model. So the idea here is that when I'm fitting my linear regression, right, I'm essentially doing a bunch of linear algebra behind the scenes, but on some level that linear algebra sums up to minimizing the error between my true energy, which I'm given as my Y train set, and the current output of the parameters and the microstates corresponding to each error, right? So on some level, when I'm doing linear regression, I'm trying to minimize this loss function. It just so happens that for this unconstrained version of this problem, the solution that minimizes this loss, so I take the derivative with respect to J, it ends up being a matrix equation, so I can write this as just inverting a series of matrices. And I show that linear algebra in the homework assignment. So the idea is that I'm minimizing basically the difference between my predicted energies and the actual energies for each training point that I give my model. So the idea is I just add a term to this loss function that basically penalizes certain properties of this J matrix. So the two most common ones that you're going to see are going to be the lasso regularizer. So this is something that's called L1 regularization. So basically I add a penalty term where I want the sum of the absolute value of the elements of this matrix here. I want those to be as low as possible, right? So I basically penalize this matrix for having a bunch of non-zero values. So in a sense, it encourages sparsity. So that's one thing I could do. Another kind of regularizer is called the ridge penalty. Here, instead of using the sum of absolute values or the L1 metric, I use the L2 metric. So I penalize the sum of squares of all these matrix elements. So these are two different regularizers that basically penalize the parameters of my model, right? So my input-output agreement is still captured by the mean squared error here. I just add on this penalty to this loss function that just describes J. And then adding these penalties into the loss is going to constrain the values of J that I get when I try to minimize this loss function. Okay. So these are two different ways of doing this penalty. They both act exclusively on the parameters. I'll talk a little bit about why you might use one or the other, but first I just want to show what happens when you add these to the model. Okay, so when I add just this penalty, J, that's called lasso regression. And then when I add the J element squared penalty, that's ridge regression. Okay, so here what I'm going to do is I'm going to fit my model and I'm going to see how well I do recapitulating this matrix in my estimated parameter matrix. So this is my ground truth that I happen to have access to because I have a lot of experimental access to this system because I simulated it. This is going to be the output of my target, and I'm just going to see how these different regularizers affect my final prediction after I fit the model with these different penalties. So these are all built into scikit-learn, this machine learning package. So I'm going to initialize this linear, ridge, and lasso models. There's one ambiguity I'm going to have to resolve is how much I'm going to penalize these terms versus the mean squared loss. So I end up picking up a hyperparameter or a free parameter in my model that determines the strength of these penalties. And for now, I'm just going to sweep a bunch of different values of that penalty parameter. So I'm basically, as I increase lambda, I'm going to fit models that have larger and larger penalties on either the sum of the absolute values or the norms. So basically, we're going to go from a limit where these are not very active to a limit where they sort of dominate the fitting dynamics. Okay, so you can do all that. You can look through my code, but this is basically just fitting a bunch of models, each with a different value of the ridge and lasso penalties, and then plotting just the output matrix. I'm just doing this a bunch of times in this loop. So when I start at relatively low values of lambda, you can see that I kind of don't get much change. Like lasso does something kind of interesting, but really you can see that these penalties aren't really acting insofar as basically my least squares without constraints gives me the same value as ridge, right? They both are these matrices that have a lot of elements in them. Lasso does something weird, but I still have a lot of non-zero entries. So none of these matrices are sparse at low values of these regularization penalties. So then as I go down the line, I'm going to gradually start increasing the value of this penalty. And you can see that basically with even sort of minor values of this penalty, lasso basically immediately finds the correct solution. So this is a correct nearest neighbors coupling matrix. Meanwhile, ridge didn't really improve that much. And so in fact, I can keep going, and it turns out that lasso is stable even if I am an order of magnitude off with how much I weigh this penalty. So I have some wiggle room here with how I choose this penalty. That will still give me a good estimate of this underlying J matrix. Meanwhile, ridge is still not working. So it keeps going. I go up another order of magnitude. Lasso still gives me a very nice answer. Ridge is still failing. Once I get to high enough values of lasso, then I start to have too much constraint active because now I start zeroing out elements of my interaction matrix that I know should not be zero. So now this penalty is sort of too strong and it's causing me to get non-physical J matrices. One question you might have is how it picks which of these elements to go to zero. I think it basically has to do with how often that interaction was seen in the training data. So this isn't like a physical effect, it just is an effect of the subset of the data that we train on. So then I keep going and I end up with basically a completely zero matrix with lasso. So that tells me that that penalty just crushed all the elements of J to zero. So now I've probably over constrained, and I bet that my test accuracy is pretty low. And in fact, you can see my test accuracy, my R squared is negative, which is usually really, really bad. Um, Conversely, like you can see my R squared actually was super high when I got the right coupling matrix. So I sort of over constrained, and now my test error actually starts to get worse. Meanwhile, you can see that ridge really isn't doing much. It's not really improving at all. Okay, so what does that tell me? That tells me that I have this fudge factor, I call it a hyperparameter, that tells me the amount to which this constraint is active and affecting my results. And unfortunately, I need to be thoughtful with how I set the parameter because you can see that if I have too little of the penalty, it doesn't do anything. If I have too much of the penalty, it'll basically be the only thing that's active and I won't actually fit my x equals y problem. And you can see that as I really get out here, I even start to zero out the elements of the matrix under ridge. So I really get into this bad regime. So there's a regime in Lambda where I have enough of this penalty that it seems to work perfectly. The problem is, how would I know if I didn't have access to the ground truth of this matrix? How would I know that this was the right choice? And the clue here would be, even if I don't know what this matrix should look like, I know that having a test accuracy of 1 is good. And so basically, without knowing what this matrix should look like, I can guess that the best choice of my hyperparameter lambda is going to be the one that maximizes my error on data that the model was not trained on. So on the held out data, I want to maximize my accuracy. I do that by checking a bunch of parameter values and picking the parameter value that maximizes my error metric on data that the model hasn't seen before. Okay, so that's ordinary least squares, ridge regression, and lasso regression. So here I'm just taking those plots I just showed, and I'm just plotting how the test error as well as the training error varied as a function of lambda. So for ordinary least squares, there's no constraints active. So my my training error stays at 1, right? Because I can just overfit and fit and get everything perfectly. My test error basically stays at 0.5. There's no dependence on lambda because lambda doesn't appear in the loss. With ridge regression, I basically get the same result as ordinary least squares. I have the same test error and the same training error, with the one caveat that when my regularization gets super big, then the elements of J basically go to 0, and so then both of these degrade. So that's a pretty bad outcome. So then lasso shows me what I want to see, which is that for lasso, my test error starts out being higher, or equivalently, my test accuracy starts out being lower than my train accuracy. However, there's this magical regime in lambda where my hyperparameters were tuned just right. That tells me that this is probably the regime where I have the correct amount of regularization, and then past there I sparsified J too much, and now my error started to suffer. So then even if I knew nothing about what J should look like, I would basically make a plot like this where I plot my hyperparameter lambda as a function of my test error, and then I see where I get this little peak, and that tells me that that's the right choice of this lambda value. One fine point I'll get into that practitioners should be aware of is technically I should be doing this on, I'm calling it test here, but really it's more of a validation set where I'm training on one set of data. I'm then choosing hyperparameters on a set of data I've never seen before. I'm calling that test, but really that's more of a validation set. And really you should have even more data you've held out, which has a single purpose, which is when you report the final accuracy of your model then sees that data the first time. And that's just so you avoid sort of effectively fitting your model to your validation data. Because when you're fishing in hyperparameter space on this data, you're effectively fitting a model to that data. So I'll mention that sometimes it's not just about train and test splits. Really, you need a train, a validation, or hyperparameter tuning fold in a separate set of data that you basically never touch until the time has come to write your paper and report the accuracy of your model. Okay. So that's about what I wanted to say about this linear regression problem. In the next lecture, I'll talk a little bit more about hyperparameters validation sets as well as cross-validation. But the takeaway here is that linear regression seems like a simple model, but sometimes when I have a prior for believing that my model has linear structure, linear regression might actually be the optimal choice. So here, I knew that my Hamiltonian depended on nearest neighbor interactions. I just didn't know what those interaction strengths were. So because that particular Hamiltonian can be written as a matrix equation, it ended up to being a really, really good choice to just fit a linear model. Picking some fancy neural network would have been both less interpretable and would have been sort of inappropriate given what I know about the nature of the structure of this problem. Fitting a linear model will give you an answer that might be very accurate on train, but you really need to look at test to decide whether you're overfitting or not. And if you are overfitting or your model is getting very, very different values of train accuracy and test accuracy, then you might start thinking about whether you need to regularize your model by adding constraints to the parameters to effectively reduce the number of free degrees of freedom in your model's parameters. Here's the different elements of J, such that your model has enough constraints that your error on the test starts to approach your error on the train. And so you can think of the gap between your training error and your testing error as sort of an ad hoc way of estimating how much you're overfitting. Okay, so that's why I wanted to talk about linear regression. It's the first of many supervised learning algorithms, but the basic idea of fitting X to Y, checking for overfitting, trying to decide hyperparameters which decide the space of possible models, all of those basic principles are going to show up in all of the other supervised learning algorithms we're going to see, even much more sophisticated ones. Okay, so I'll go ahead and wrap up there.